Hello everyone, myself Venu and lecturer in mechanical engineering from Government Polytechnic Varangal. So today's video lesson, the topic goes on analysis of pH diagram and TS diagram of vapor compression refrigeration system. If you observe in the previous class, I think I have learned the working of the principle of a VCR system and working of a VCR system and seen some applications of a VCR system. So how we are getting the refrigeration effect in the vapor compression refrigeration system. So in today's video lesson, we will analyze the pressure enthalpy chart and temperature entropy chart of a VCR system at each and every stage, at each and every component, means compressor, compression, and in condenser, condensation, and expander, expansion, and in the evaporator, evaporation process. At each and every process, how the pressure variations are taking place and how the temperature variations are taking place, and what is the enthalpy and entropy, all the things we can analyze in this pH and TS diagrams. So just have a look regarding some points regarding the previous video lesson. Principle and working already discussed regarding that. Hope you understood the topic. And next, the various parts we have seen, each and every part functioning in the VCR system and applications of VCR system we have seen. And next, in today's video lesson, you will be able to understood the following topics: the pressure enthalpy diagram of VCR system, temperature entropy diagram of VCR system, and make the analysis regarding this TS diagram for VCR cycle and pH diagram of VCR cycle. We'll see some mathematical formulas regarding that to find the enthalpy, that means the total heat, and the entropy values. See that, right? So have a look regarding this pressure enthalpy chart. So just look at all the points and all the names mentioned in the graph. So on the x-axis or on the x-coordinate we are mentioning the enthalpy values, and on the y-ordinate we are mentioning the pressure values. And some more terminology we will learn one by one. You can see a curve is drawn here, where you can see the curve. So starting from the axis, x-axis and y-axis origin, so that is a saturated line. You can see the curve, saturated line, and at the left hand side and at the right hand side, if you observe, there is a saturated vapor line. So it is both the liquid line and vapor line saturated. They are meeting at a point known as a critical point here. The lines are mentioned as saturated liquid line and saturated vapor line at left and right side of the chart, and meeting point of both the lines is named as critical point. And three regions here you have to mention in this chart. You can see before the saturated liquid line there is a super cooled liquid region, and in between the saturated liquid line and saturated vapor line, the region which is present below this curve is a wet vapor region. And after the saturated vapor line, the region is a superheated vapor region. You will see what is the importance of these terminology and why the graph is taken like this, and what is the importance of these lines. And try to remember the pressure enthalpy chart, where the x-ordinate is enthalpy, y-ordinate we have taken the pressure values. So the critical pressure is mentioned at a particular point, that is at the critical point we can measure the critical pressure. Right. So we will see some point wise regarding that. So discussed points are that pressure is plotted on the vertical ordinate and enthalpy is plotted on the horizontal ordinate. Right. Okay. And next, you can read that line: the saturated liquid line and saturated vapor line match at a critical point. Already discussed this thing. Both the lines which are passing at left hand side and right hand side, you can see the curve. Both the meeting points where you are taking that point is a critical point. Measuring the pressure at that point is critical pressure. So the already discussed the point is the diagram is divided into three regions: super cooled or subcooled liquid region, wet vapor region, and third one is superheated vapor region. So these are the three regions: subcooled, wet vapor. Subcooled liquid region means completely the whatever the fluid you are taking or the refrigerant is completely in the form of liquid, and within this curved region, below the curved region, that is a wet vapor. It means the combination of liquid plus vapor. Whereas the superheated vapor, it means it is crossing the saturated stage of vapor, and the vapor which is present in this region is superheated form at that superheated temperature. And you'll see the regions one by one. Subcooled liquid region is the region to the left of the saturated liquid line. The left you can see the region which is present at the saturated liquid line. The temperature of the liquid is below the saturation temperature corresponding to its pressure. So whatever the temperature of the liquid is there, it is below the saturation temperature. So here there is the saturation of liquid will starts when it reaches this line. So the temperature which falls, which is not reaching at the saturation point, and the temperature which falls in the subcooled region is taken as the subcooled. That is, it is below the saturation temperature corresponding to its pressure. So taking a reference to the pressure, the temperature is, you can see, or you can plot in the graph where it is less than the temperature is less than the saturated temperature. So the heat, the total heat is a sensible heat. So whatever the heat carrying in this region, it is a sensible heat. It means there is no change in the phases taking place. The total heat carried in this region is the sensible heat, which is denoted by H. Next, second region is the wet vapor region. So already discussed that the space between the saturated liquid line and saturated vapor line, that region is wet vapor region. So this region represents the phase change of refrigerant from liquid to vapor. So in this region you can observe there is a slight change in the phase change is taking place from liquid refrigerant to the vapor refrigerant. Right, and here you see how the total heat in the subcooled region is represented as H, whereas the total heat or enthalpy in the wet vapor region is, so it is represented with HW, which is equal to H is a sensible heat carried by the liquid plus X into L. So we will see those points. H is, small h is the sensible heat of the liquid. So some of the liquid content is present in the wet vapor region. And next, X is the dryness fraction. So whatever the vapor, the conversion of the vapor of refrigerant is taking place, that vapor refrigerant is carrying some dryness. So that represented in the fraction form. So that is represented as X. L is the latent heat of the liquid. So these are the terminology how we will find the enthalpy at that particular pressure point. This is the formula: HW equal to small h plus X into L. For saturated vapor, it must, right. So here the total conversion will take place instead of wet vapor when it reaches the point, when it reaches on the curve, means it is reaching to a stage of saturated vapor, complete saturated vapor. So on the curve at the right side, if you observe, then the dryness fraction X will become it equal to 1. So the total heat is can be taken as HS for saturated vapor. It is equal to H plus L, small h plus L. Next, third region is a superheated vapor region. So the space on the right side of this saturated vapor line, this is the saturated vapor line at the right side. So above this, the region present is the superheated vapor region, where the total heat or enthalpy can be found by using this mathematical formula. It is represented as H sup, which is equal to small h plus L. Small h is a sensible heat, L is the latent heat, plus Cp into T sup minus Tz. Cp is the, you can see the terminology here, it is equal to nothing but the specific heat at constant pressure. Cp is specific heat at constant pressure. T sup is the temperature of superheated steam. The Tsat is saturation temperature at the given pressure. So T soup short form is a superheated superheated in terms of steam, or it can take it as a refrigerant here. Superheated refrigerant temperature, that is a T soup. Tsat means saturation temperature at a given pressure of that particular refrigerant. So this is the formula for superheated or a total heat or enthalpy at the superheated region, H plus L plus Cp into E soup minus Tsat. Here the dryness fraction will not present. Why? Because completely it is in the form of vapor. Right. So this is the temperature entropy chart. Till now we have seen the pH chart, pressure enthalpy. Next we will see the TS chart, temperature entropy chart. So observe here again on the x ordinate. If you observe, you have taken the entropy, and on the y ordinate if you observe, absolute temperature is taken here. So the curve you can see the same thing again. There is a liquid line at the left side if you observe the liquid line, and this curve is meet at the critical point where it is making contact with the next other side of the right side of the curve, that is the saturated vapor line. Again here you have to discuss the same points here. If you observe, absolute temperature is plotted on vertical ordinate as earlier discussed, and entropy is plotted on horizontal ordinate. So three regions are divided in this, similar to pH chart. TS chart is also divided into three regions. Next, subcooled region. We discuss the region wise. The entropy of liquid in the region is given. You can see the entropy is plotted on the x-axis. So the subcooled region is there to the left of the first curve, that is the liquid line or a saturated liquid line. That is a S1 equal to log base E T by 273. So where here the T is the absolute temperature corresponding to the pressure P at which the phase change starts. T is the absolute temperature corresponding to the pressure P where the phase change starts. Next, second region, wet vapor region, the change in entropy is taken as change in the entropy, which is equal to x into L by T, that is absolute temperature, L is the latent heat. So the entropy of wet vapor in this region, entropy of total wet vapor is represented as SW. You can see the formula, which is equal to S1 plus x into L by T, that is the change in entropy is x into L by T. S1 is already we have seen that is the entropy at the subcooled region at particular pressure. So S1 plus x into L by T, so which is equal to, it can be also written as S1 is nothing but log base C T by 273. T is the absolute temperature plus x into L by T. Next, the total entropy of saturated vapor. So when it reaches the saturated vapor line, total entropy can be written as, where you cannot see the dryness fraction. Very simple, x will not be there, x undadandi, right? So SW equal to S1 plus L by T, so which is equal to S1 already we have written the log base C T by 273 plus L by T. So very simple formula. Then reaches to the next third region, that is a superheated vapor region. The change of entropy, so which is equal to Cp log base E T sub by Tsat. That is a change in entropy. And if you observe the superheated vapor region, the total entropy of superheated vapor, how to find the S soup, represented as S soup, superheated vapor entropy, which is equal to S1 plus L by T plus Cp log E T sub by Tsat. Not that is it is a T absolute temperature. So S1, or in place of S1 the same formula can be written as that log base E T by 273 plus L by T plus Cp log base E T sub by Tsat. So here you can find the entropy, total entropy of superheated vapor by using this formula. Right. Next, after looking the TS and pH and TS diagrams, so we will make the analysis of the process happening in the pH and TS diagrams. Next, we will see the mathematical relations for that, right? So this is a PV diagram. You can observe the PV diagram here, and see the processes from 1 to 2, that is isentropic compression process, where this process is taking place in the compressor, and 2 to 3 is the isobaric condensation or constant pressure condensation process, which is happening in condenser. You can observe the line from 2 to 3 is a constant pressure. You can observe on the graph also. So V volume is plotted at the x-axis, and the pressure is plotted at the y ordinate, and 3 to 4 is the isenthalpic expansion. It means that it's a constant enthalpy process. So here the expansion will take place in the expansion device. Next, 4 to 1 is the isobaric evaporation. 4 to 1 is here it is not mentioned clearly. 4 to 1 is the isobaric. Again, the constant pressure evaporation is taking place. Okay, constant pressure evaporation is taking place. If you observe the temperature entropy diagram, this is a temperature entropy diagram. You can see all the temperature, the 1 to 2. I will show it in another diagram very clearly. You can see this the textbook diagram clearly. This is a temperature entropy diagram of VCR cycle. So 1 to 2 process, 2 to 2 dash, 2 dash to 3, 3 to 4, and 4 to 1. So you can take 4 complete processes, reversible process, 1 to 2, 2 to 3, 3 to 4, 4 to 1. And again 1 to 2 representing isentropic compression, 2 to 3 is condensation, 3 to 4 is throttling process or expansion, and 4 to 1 is the evaporation process. So here you can observe the from 2 dash to 3, here it is a constant temperature process, and whereas here phase change is taking place in 2 dash to 3, and if you observe from 4 to 1, it is also a constant temperature process where the evaporation is taking place. We'll see it. Okay, next the diagram, pH diagram. Here the 1 to 2 process, and 2 to 3 is a constant pressure process. 1 to 2 is a the compression process taking place where the pressure is increasing. So we will discuss it clearly one by one. So this is how the diagram is drawn: 1 to 2, 2 to 3, 3 to 4, and 4 to 1. As we have seen, the 3 to 4 is isenthalpic process. So constant enthalpic process is 3 to H4. Okay. So this is a pH diagram, pressure enthalpy diagram of VCR cycle. You can observe the 2 to 3 and the 4 to 1 process. Those are the constant pressure process. 3 to 4 is the isenthalpic process. It is a constant enthalpy, H3 equal to H4. Now the process description, here we can explain very clearly. Again, the same temperature entropy diagram is drawn here. So first we will see the process. What is happening in process 1 to 2? So isentropic compression of vapor in the compressor. Entropy of vapor remains constant. What is happening here? Compression of vapor isentropically take place in the compressor, and here the entropy remains constant. That means S1 is equal to S2. And what about the temperature? From point 1 to point 2, temperature is increases. Next, the process 2 to 3, if you observe process 2 to 3, what is happening here? Condensation of vapor in the condenser take place. So constant pressure process, and here the pressure remains constant, and refrigerant is rejecting heat to the surrounding, changes its state from vapor to liquid. Okay, the refrigerant is changing its phase from vapor to liquid. That is a condensation process which is happening, constant pressure process that will take place in the condenser. We'll see what is the 2 to 2 dash and 2 dash to 3 clearly, and we'll see in the analysis. First we will discuss the process here. And 3 to 4 is the expansion of liquid refrigerant in the expansion valve. That is a throttling process or isenthalpic process, constant enthalpy process. So enthalpy remains constant here. Next, the 4 to 1 process is evaporation process. Evaporation of liquid in the refrigerant in the evaporator will take place, and it is a constant pressure process. So liquid refrigerant absorbs heat from the products, as I earlier discussed regarding this process, and changes its state from liquid to vapor. So in the condensation, what is happening? Vapor to liquid, and in the evaporation, it changes its state from liquid to vapor. Temperature of the space to be cooled is reduced. Next, we will see the thermodynamic analysis by taking the same TS diagram. What is happening in the process 1 to 2? Low pressure and low temperature, the dry and saturated vapor refrigerant enters the compressor at point 1. So that is from the after evaporation, very low pressure and low temperature, dry saturated refrigerant enters at the point 1 here. It means at the compressor entry. Compression will take place in the compressor, and what happens here, after compression the pressure rises, very high pressure and high temperature vapor refrigerant, it is discharged. It take place at the exit is at the point 2. Very high pressure, you can see temperature is rises due to the high pressures are created in the compressor. So work done on the compressor, work done on the compressor is, you can take it as H2 minus H1, H2 minus H1. So entropy is constant here, S1 equal to S2. This is the thermodynamic analysis. And if you observe the second process 2 to 3, high pressure and high temperature vapor, after compression it enters the condenser at point 2. So constant pressure, heat rejection is taking place here. It's a constant pressure process, and heat rejection will happen in the condenser. First observe here, 2 to 2 dash is a condensation of superheated vapor to saturated vapor. Already discussed this region. So 2 is present in the superheated region, and 2 dash is falling on the saturated vapor line. So this is the process which is happening. First, the superheated vapor is turning to the saturated vapor. So this is the representation of the process 2 to 2 dash. So 2 dash to 3 is the condensation of the saturated vapor which is present. The line name what it is discussing, it is a saturated vapor line. That condensation of vapor take place to the saturated liquid up to the point 3, that is a 2 dash to 3. Here the refrigerant rejects heat to the surrounding water medium, and changes its state to liquid. Phase change is occurring in this condenser part here. Next, during process 2 to 3, high pressure, low temperature liquid refrigerant. Here the phase change is taking from vapor to liquid. Pressure is remaining constant, and low temperature refrigerant is delivered to the expansion valve at point 3. So here the throttling take place. Heat is rejected by the refrigerant in the condenser. Next, that heat rejected by the refrigerant, in terms of enthalpies you can write it as H2 minus H3, and the heat gained by cooling medium. So heat is received by the cooling medium, what may be water or air. So it is gained the heat from the refrigerant, and the refrigerant changes its phase from vapor to liquid. That is regarding the process 2 to 3. So the heat gained by cooling medium, so that is a simple formula, it is MC delta T. And the process 3 to 4 is a throttling process, where the high pressure, low temperature liquid refrigerant enters expansion valve at point 3, and the liquid refrigerant is further expanded by throttling process in the expansion valve. What happens here, the isenthalpic expansion will take place. It is a constant enthalpy process where the value is H3 is equal to H4. Okay, H3 equal to H4. So no work is done during this process. Low pressure, it means no work is obtained here. So low pressure, what happened here, only the temperature drop will take place, rapid temperature drop. So low temperatures are created after the expansion device, where it enters at the point 4. It means to the evaporator. So discuss the 4 to 1 process. So low pressure, low temperature liquid refrigerant enters at the point 4, the constant pressure heat absorption from the products in the evaporator. So here what happens, the constant pressure process is 4 to 1 where the evaporation is taking place. That means heat is absorbed from the products by the refrigerant in the evaporator part. And during this process, the liquid refrigerant changes its phase. In the condenser, the first phase change is taking place. In the evaporation, the second phase it is changing from liquid to vaporized form. So low pressure, low temperature, the dry and saturated vapor refrigerant enters again into the compressor at point 1. What happens here? Again changing its phase to vapor form, that completely dried out, and that vapor refrigerant enters at the compressor at point 1. So this is the processes, thermodynamic analysis. We're taking the reference of the temperature and entropy diagram. So it is a cyclic process which is taking place from point 1, 2, 3, 4. Again this processes are repeating again and again. So since evaporation takes place at constant pressure, pressures are equal, P1 equal to P4, temperature is equal, T1 equal to T4. So heat absorbed or refrigerating effect. So you are getting the cooling effect during this process 4 to 1, or the refrigerating effect. So heat absorbed equal to, or cooling effect equal to, H1 minus H4. Since so H4, we have seen that isenthalpic process 3 to 4. So H4 equal to H3. So you can write that as refrigerating effect equal to H1 minus H3. So this is regarding so here we can find the COP of refrigerating effect, VCR system, that is COP equal to refrigerating effect by work done. So what is COP? Coefficient of performance. Refrigeration, already we have seen this formula. COP, output is the cooling effect and input is the work done on the compressor. So work done, already we have seen the formula is H2 minus H1. Refrigerating effect is the heat absorbed in the evaporator, that is H1 minus H3. So this is a COP formula. Please try to remember this formula to find the performance of a vapor compression refrigeration system in terms of enthalpies. Right. So coming to the summary, we have seen regarding the pH and TS diagrams and the representation of VCR cycle on PV diagram, TS diagram, PS diagram, thermodynamic analysis, process descriptions, and we have seen the COP formula of VCR system. So lot of things we have seen in this, and we have seen analysis of these diagrams or these graphs. We have seen again the same process, and we have seen some formulas regarding that, how to find the COP. And here we have the quiz, so you can read out these things. The thermodynamic process takes place in the compressor is isobaric, isothermal, isentropic, and isenthalpic. So in the compressor, it is, answer is isentropic compression process. That is the answer is C. Similarly, the next question, the thermodynamic process takes place in the condenser is, it is a isobaric process. It means constant pressure process, right? So it is a, answer is A, isobaric. Next, thermodynamic process takes place in the expansion valve. So what is that? It is a isenthalpic process, constant enthalpic process which takes place in the expansion device. Next one is thermodynamic process takes place in the evaporator is, the first one is isobaric, isothermal, isentropic, isenthalpic. Again the evaporation, it is also a isobaric process or constant pressure process, right? The answer is isobaric or constant enthalpy process. You can see some, so regarding this quiz and frequently asked questions. So represent the VCR cycle on PV diagram, on TS diagram, explain VCR system with the help of pH diagram, pressure enthalpy diagram. So try to remember those regions, very important regions, and lines what you are connecting at a critical point at the left hand side and right hand side. So practice it, it will be very helpful, and you can explain in any way the VCR cycle with the help of these diagrams. So hope you have understood the complete vapor compression refrigeration system in the previous video lesson, and this session we have seen the complete thermodynamic analysis on based on the pH diagrams, PV diagram, and TS diagram of a VCR system. So we have understood. So we'll see in the next video lesson, and thank you. further we will see the pressure enthalpy diagram in a graphical representation way in this video.
It is a graphical representation of a fluid state variables and allows visualizing properties of fluids in a state and during a process. The diagram is often used for engineering refrigeration units and heat pumps. The pressure enthalpy diagram shows the absolute pressure P on one axis and the specific enthalpy H on the other axis. The absolute pressure P in a fluid is the force per area the fluid exerts on a wall or on adjacent parts of a fluid. In order not to confuse absolute pressure from relative pressure, which is often used in practice, the unit bar is sometimes used with an additional A for absolute. The specific enthalpy H is the energy per unit of mass a fluid transports across a system boundary. We explain in another video that enthalpy H is composed of internal energy U and the work needed to move a mass of fluid across a system boundary, which is given by absolute pressure P times the specific volume V. The absolute pressure P is plotted on the vertical axis. The specific enthalpy H is plotted on the horizontal axis. Each point in the diagram corresponds to a state of a fluid. Its state variables have certain values: pressure P, temperature capital T, specific volume V, specific enthalpy H, and specific entropy S. Lines with constant specific enthalpy H are called isenthalpic lines. They stretch vertically because H is plotted on the horizontal axis. If a state of a fluid changes from state A at constant specific enthalpy H along an isenthalpic line to state B, we call it an isenthalpic change of state. Lines with constant pressure P are called isobaric lines. They stretch horizontally because P is plotted on the vertical axis. If a state of a fluid changes from state A at constant pressure P along an isobaric line to state B, we call it an isobaric change of state. While the specific enthalpy H on the horizontal axis is shown in a linear scale, the pressure P on the vertical axis is shown in a logarithmic scale. This can be seen in the distribution of the isenthalpic and isobaric lines. We now are looking at the pressure enthalpy diagram of R134A, a widely used refrigerant. We can see that the plane contains many lines in different colors, which are arranged in a chaos at first sight. For experts, such a diagram is a map allowing to see the behavior of a fluid at a glance. We are going to explain what these many lines actually mean. A pressure enthalpy diagram contains a dome-shaped area. It stretches from the line of saturated liquid on the left to the line of saturated gas on the right. Both saturation lines meet at the top in a critical point. To the left of a saturated liquid line, the fluid is in a liquid state and the specific enthalpy H is low. This is the area of a liquid phase. To the right of a saturated gas line, the fluid is in a gaseous state and the specific enthalpy H is high. This is the area of a gas phase. In the dome-shaped area between the lines of saturated liquid on the left and saturated gas on the right, both the liquid and the gaseous phases exist simultaneously. It is called two-phase domain or wet steam domain. If the fluid consists of a single component, the state in this domain is a mixture of a saturated liquid and a saturated gas in thermodynamic equilibrium with each other. In the left part, most of a fluid is liquid and only a small amount is gaseous. In the right part, most of a fluid is gaseous and only a small amount is liquid. Lines of constant vapor content X are indicated in the two-phase area. The vapor content X is the mass ratio of a gaseous fluid and is also called quality. If a state of a fluid moves from left to right in the two-phase domain, the quality X increases from 0 to 1 and the fluid is evaporating. If a state of a fluid moves from right to left in the two-phase domain, the quality X decreases from 1 to 0 and the fluid is condensing. If a state of a fluid is above a critical point, it is called a supercritical fluid or a supercritical gas. The transition from the liquid phase or the gaseous phase into the supercritical domain is not sudden but smooth and continuous. If points with the same temperature are connected with each other, the isothermal lines become visible. In the two-phase domain of a pure substance, the isothermal lines are horizontal and run parallel to the isobaric lines. This means that in the two-phase domain of a pure substance, for example during evaporation or condensation, pressure and temperature are coupled with each other. If a state of a fluid changes from state A at constant temperature, capital T, along an isothermal line to state B, we call it an isothermal change of state. In each point of a diagram, the fluid has a certain specific volume, V, which is a volume per unit of mass of fluid. If points with the same specific volume are connected with each other, the isochoric lines become visible. If a state of a fluid changes from state A at constant specific volume V along an isochoric line to state B, we call it an isochoric change of state. In every point in the diagram, the fluid has a certain specific entropy, S. It is a measure for reversibility of processes. If points with the same specific entropy are connected with each other, the isentropic lines become visible. If a state of a fluid changes from state A at constant specific entropy S along an isentropic line to state B, we call it an isentropic change of state. This is the case if no heat is exchanged between system and environment and only reversible processes take place in the system. All these characteristics from different fluids can be shown in a pressure enthalpy diagram. What refrigeration experts call R134A is called 1112 tetrafluorethane by chemists. Now we see a pressure enthalpy diagram of methane and many other refrigerants. More about the practical usage of a diagram like this will be shown in part 2.
Continuation of this session, we will see the types of compressions also. It means how depending on the state of the refrigerant entering into the compressor, what we have seen the three different regions. So for example, if the refrigerant is it's entering with some dry saturated vapor form, or a combination of wet vapor form, or a superheated form. So all the things can be seen in this session. So depending on the state of refrigerant. So here the compression could be wet compression and dry compression. First is the wet compression. The condition of refrigerant vapor is wet at the entry of the compressor. So if you see the graphical representation, at what state the refrigerant is entering into the compressor. So we will look at the pH diagram. So already we have seen in the session, and here if you observe at the point 1, so the refrigerant this point 1, so this falls under the region of wet vapor region. So the point 1 is present in the wet vapor region. So the compression happening here is wet. Why? Because some wet nature of refrigerant is or some liquid form of particles of refrigerant is present during the entry of the compressor. It is not completely saturated, the refrigerant. So this is the diagram we are drawing. So after completion of compression also, you can see it is present at the exit of the compressor. It consists of some liquid particles. It is not completely saturated after compression also. Pressure is raised, but the liquid particles are present in this. This is the TS diagram. If you observe, again the same at point 1. So what happens here at 4 to 1, the refrigeration effect is getting reduced. If it starts from on the saturated vapor line, the refrigeration effect will be more from 4 to 1. So here the 4 to 1, this entry of the compressor is decreased here. It means it is not completely saturated vapor form. It is having some wet nature. The refrigeration effect may get reduced. and it is isentropic process 1 to 2, you can represent here in TS diagram. Right. So what happens, we'll see some disadvantages when the refrigerant is in the vapor form or in the wet form, and if it enters into the compressor. What happens here? The first thing is incomplete evaporation of refrigerant in the evaporator. So it means before the enter of the compressor, you see there is an incomplete evaporation of refrigerant is taking place in the evaporator. So due to incomplete evaporation, complete vaporization is not possible in the evaporator. Then along with liquid particles, it is entering into the compressor. So it means it is also resulting of a loss of refrigeration effect. The liquid refrigerant trapped in the head of the cylinder. So whatever the liquid particles of the refrigerant is there, so in the cylinder part of a compressor, so it will be trapped there. So further the problem will be arise. The moisture content or liquid particles may damage the compressor valves and the cylinder head. More the noise is created, there is a chance of busting also. So here it will, whatever the lubricant oil present in the compressor, so it will be washed away, and due to that no lubricating oil, the wear and tear will take place of the compressor cylinder. So it will cause there some hammer blow, more noise is created, and it leads to the busting of compressor. And during the suction stroke of the compressor, liquid particles evaporate. This is also the one problem. It evaporates and it will reduces the volumetric efficiency due to during the suction stroke of the compressor, completely the liquid particles evaporate. So what happens, thus reducing the volumetric efficiency. And next one is a dry compression. So it mostly happens when it reaches the entry of the compressor of the refrigerant is in the form of dry state or dry vapor, dry and saturated at the entry of compressor. If you observe the diagram here, so observe, compare with the previous case, that is wet compression, it is not completely saturated form. So here if you observe dry compression, the point 1 is present on the saturated vapor line. So this is representing the dry compression. So after compression, if you observe at the exit of the compression, you can see the vapor is in the superheated form. You can see this region at the right side of the saturated curve, you can see this region is superheated region. So at the end of the compression, the vapor is superheated. So compared to wet compression, so dry compression is better, more refrigerating effect you are getting. And this is again the TS diagram. So you can see here a constant entropic process here 1 to 2 2 dash, vapor is superheated at the end of the compression. This is the TS diagram for TS diagram for dry compression process. And here few points has to discuss. The condition of refrigerant vapor is superheated at the entry of the compressor, then also the compression is called dry compression. For example, if you are getting the superheated vapor entry into the compressor, so that type of compression can also be taken as the dry compression, the very starting of the entry of the compressor. The VCR cycle with superheated compression is represented on pH and TH diagram. It is, you can see the same thing for superheated case. It is also known as the dry compression, but the entry of the compressor is at the superheated form. You can see at the end here, one dash here, one double dash. See, the entry of the compressor is in the superheated form of vapor. Superheated compression. And at the end also, if you observe after compression, it is also completely in the form of, it remains in the stage of superheated vapor only at the end of compression also. Right, so this is the diagram for when the refrigerant is entering superheated form. Right, in superheated compression, the vapor remains superheated at the end of the compression. As already discussed, you can see the point second 2 double dash where it is in the form superheated at the end of the compression also. It results in more refrigeration effect, but obviously the compression work from 1 to 2, compression work will also increases. So resulting more the compression work means what happens, more than the refrigeration effect. If compression work is more than the refrigeration effect, so obviously the COP may decreases. So that is one reason here why it is very undesirable case. So not choose this type of case. You are getting more the refrigeration effect, but obviously you can observe the 1 to 2 process, it is a work done on the compressor is also more when compared to the refrigeration effect. So obviously the COP will get decreases. So coming to summary, just two topics we have discussed, that is regarding wet compression and dry compression, and wet compression disadvantages we have seen, and superheated compression is also seen, and some pH and TS diagrams regarding the wet compression and dry compression is seen here, right? So coming to the quiz part here, you can see some few questions. The state of refrigerant before compression in wet compression is, so obviously it is wet nature. Next, the state of refrigerant after compression in dry compression is, so after compression it is got superheated. After compression, first it is dry compression, during entry at the exit it is superheated. So the state of refrigerant before compression in superheated compression, again it is entry it is superheated, at the exit of the compression is also superheated. So both the cases it is in the form of a superheated, more the temperature is increased. So the effect of wet compression or refrigeration effect. So what happens, we have seen the process 4 to 1. So the value is getting decreased, the graph if you draw, the value is getting decreased, right? So enthalpy in between those, the total heat in between those is less. It means the heat absorbed by the particular refrigerant during the process 4 to 1 is less, right? So what is the answer will remains here. So obviously the refrigerating or cooling effect get decreases due to the wet compression. Must and should be dry compression process, it would be somewhat better. So these are the few questions. What is wet compression? Explain with pH and the TS diagrams. What is dry compression? Explain with pH and TS diagrams. So compare wet compression and dry compression. So you can compare with the some diagrams, and you can notice some points in that. What happening to the refrigerating effect? What happening to the work done on the compressor? And what happening to the COP? So just pointing out some points, so you can write down what is happening there. Okay. So hope you have understood this topic. Thank you.